All right, let's jump into Power Amps Part 3 here. We're still on Chapter 12, but we want to talk now about efficiency. Okay, and basically the efficiency of any amplifier is the ratio of the signal power supplied to a load to the power from the DC supply. So ratio of the signal power to the load to the power. That should have been signal power supplied to the load to the power from the DC supply. From the okay, earlier we said maximum signal power is given by, we called it P out max. We said that was 0.5 ICQ, Q point collector current, times VCEQ, Q point VCE voltage. So the average power, supply current, okay, and we've been calling that ICC. Again, that's DC power supply current, is equal to ICQ and the supply voltage is at least 2 VCEQ. So the DC power is, we called it PDC, ICC times VCC, and that's going to be equal to 2 ICQ times VCEQ. And we can say the maximum, if we do a little math, the maximum efficiency of a capacitively coupled Class A amp is, this is really important, so we'll call it a EFF max we'll use for maximum efficiency. We said it's P out over PDC. Okay, make some substitutions, do some math, so we end up with 0.5 in the numerator times ICQ times VCEQ divided by 2 times ICQ times VCEQ, 0.25. Okay, so this is really important. This is the maximum efficiency of a capacitively coupled Class A amplifier, and it can't be higher than 0.25 or 25%. Okay, in practice, it's usually a lot less than that. It's around 10%, 0.1 or 10%. So this is the issue with Class A power amplifiers. They're low efficiency. You can make it a little higher. Let me add another page here. Let's say I'm going to put a little star here. I'm going to say this. Capacitively coupled Class A amplifier efficiency cannot be higher than 0.25, let's say, or 25%. And in practice, it's usually a lot less. Okay, typically 10% or so is pretty common. So that's low efficiency. You can make it higher. There's different ways to make it higher. Let's just mention those. We're not going to take a close look at them. Efficiency, let's say, can be made higher by transformer coupling, the signal to the load, but there are drawbacks. Using transformers. Okay, they're heavy, they're expensive, so we can say size and cost. Heavy, they're big. There's also potential for distortion. Distortion problems, let's say. So when the core transformer core begins to saturate. Okay, so low efficiency is an issue. Okay, so in general, I guess we can say the low efficiency of a Class A power amplifier limits their usefulness to small power applications that require only a few watts of load power. So why don't we say this? This low efficiency limits Class A power amps to small power, limits Class A power amplifiers, let's say, to small power applications that require only a few watts. Of load power. Okay, and what that does, this leads us now into Class A and Class AB push-pull amplifiers. Now the Class A stuff you've been doing all along, the small signal amplifier work you did all last semester, for example, it's basically Class A stuff. So let's add another page here. Let's talk now about Class B and Class AB amplifiers. Okay, sort of in general terms. Now let's talk about Class B first. Okay, Class B. Okay, we can say when an amplifier is biased at cutoff, so that it operates in the linear region for 180 degrees of the input cycle, is cut off for 180 degrees. Okay, so if we draw just a little block diagram here, see if I can do this. Okay, I'm going to draw my amplifier here. I'll put some values in here in a minute. And I'll draw another axis over here. All right. So this is our amp. AV. Okay. We've got a single signal here, VN. We've got a signal here, V out. Okay. Let's say we've got a sinusoidal input here. We can label some times. T0. Positive 0 degrees on our cycle. T1, negative going 0 crossing. T2 comes back around and starts another positive half cycle 0 crossing. Okay, our output looks like this. All we see are the positive half cycles. T0, T1, T2, etc. Okay, so this is a basic Class B operation. That's what this demonstrates. And it's non-inverting. Okay. There's no phase shift, so it's not inverting. Frequency doesn't change, just the amplitude changes. So we'll get into it a little more. We'll get into a little more detail. Class AB though, just in general, Class AB is basically, it's a Class B, but it's biased, and we'll take a closer look at these. Biased to conduct for slightly more than 180 degrees. Okay? And we'll talk about how you do that and why you do that and what that means as we get into it a little more. Now, the advantage of both of these, of Class B and Class AB amps over a Class A amp okay, either is more efficient. Okay, so you get more output. Power for a given amount of input power. Okay, so that's our advantage. The disadvantage, okay, the Class B and Class AB circuits are more difficult to implement. I'm just going to put a little $ in parentheses here. Cost more. Okay, so Class B operation. Let's go to the next slide. We just drew the picture of Class B operation, so I'm going to be referring back to this this operation diagram. Let's add another slide. Okay, let's talk about the Q point. Okay, so we're talking Class B now. cue point is at cutoff. It's no longer in the middle of the load line. Okay, so the Class B amp, we can say, is biased on purpose at the cutoff point. So that ICQ is equal to 0 and VCEQ is equal to VCE at cutoff. Okay, if you refer back to our load line, okay, this is our load line. If you remember, this is IC sat. Remember, this axis is IC, this axis is VCE, this is VCE cutoff. Okay, our cue point is right here. Okay, that's where we place our cue point. So that's the operating point for the transistor. So it's biased to operate at that point. Okay, so what can we say? Okay, so in general, let's just write something down here. We can say it is brought out of cutoff. And operates in its linear region when the input signal drives the transistor into conduction. Okay. So an example would be an emitter follower circuit. I can spell it right. There's only one emitter. 2 T's. Emitter follower circuit. I think I have enough room to do this here. So we've got VN. That's an AC input. We've got our transistor. We've got our emitter resistor. We're not sticking any caps in for now. This is VCC plus VCC. So transistor. Okay, and we're taking our output at the emitter. And what we end up with is we end up with an output. I'm just going to draw it in general terms again. That looks like this. Oops, I forgot. I just realized I forgot to draw the rest of my circuit. Okay, so our output looks like this. All we're seeing is positive half cycles. Okay, let's not worry about any values yet. Okay, so this is 0. Okay, so the circuit only conducts for the positive half cycle of the input. All right, so I can draw a another little diagram here. Let's go to the next page. Let's take a little closer look at what's going on with our input signal. I wish I had this all on one page, but I don't. All right, so we've got 0 here. Okay, here's our sine wave. Let's see if I can draw this so it's at least somewhat symmetrical. It's not too bad. Okay. I forgot to change this. Let me erase this. Redo this one again. Star axes. That was such a nice sine wave I drew too. I don't think I'm going to be able to repeat that. It's not too bad. You get the idea. Okay, so this again, the circuit's only conducting for the positive half cycle, and you've got. Let me draw another line here. I'll draw this in blue. You have to remember that base to emitter junction has to be turned on. It has to be 0.7 volts for the transistor to turn on. It needs to be a positive 0.7 volts for the transistor to turn on. So the transistor conducts when the input is greater than 0.7 volts. Okay, so this is what you're seeing. You're not seeing the entire positive half cycle of the input. You're seeing the positive half cycle of the input when the input is greater than 0.7 volts. And down here, transistor's off. Okay, so we're going to say it again, just to make sure we understand it. Notice the circuit only conducts for the positive half cycle of the input. Okay, if you want to amplify the entire cycle, okay, you must add a second Class B amplifier that operates in the negative half cycle. Okay, so basically you're combining two Class B amplifiers. So we can say that's the combination of two Class B amps working together is called push-pull. You may have heard this term before, you may not have heard it. It's a fairly common term in the world of electrical engineering. Push-pull operation. Okay, there's two ways to do this. Two common ways anyways. Okay, number one is our old friend, the transformer. Transformer coupling. And number two, using two what are called complementary symmetry transistors. All right, I'm going to stop this here, and in Power Amps Part 4, we'll take a look at these.